Hi, my name is Vivek. I work in the research team. So my talk today is going to be about, can you tune my car? This is a question that I get at least once a week on Discord. So we have a Discord. I'm sure, how many of you have been on our Discord? Okay, and we have a development tuning channel. How many of you have been on the tuning channel? Okay, great. So if you go to the tuning channel, you see a lot about good tuning, bad tuning, and ugly. Maybe not ugly, just good and bad. So if you're new to openpilot or new to Discord or new to the channel, you might be wondering what exactly needs tuning, right? So everything that we spoke about today, we never really spoke anything about tuning something. So what exactly needs tuning? And for that, you have to understand, how is your car different when it comes to openpilot? Like, how are cars different with respect to openpilot? So these are some of the brands that we support. So some ways in which cars are different are, the wheelbase is different. And the wheelbase is the distance between the front and the rear wheel. So as you can imagine, different cars have different sizes, so the wheelbase is different. They also have different widths. And as a consequence, they also have different masses. Like some cars are light, some cars are heavy. We support from like tiny cars to like the Ram, and they're quite different in that way. Cars are also different when it comes to other things like steering ratio. Steering ratio is how much your car turns with how much steering wheel turn. And that is different in each platform and also different across brands. Your tire stiffness, which is again the quality of your tire, how much torque your tire provides while turning, stuff like that is also different. The center of gravity is different in all cars. Depends on how many people are in the car and stuff like that. And then actuator lags. So each brand and each platform have different ways of processing the signal that we send to the car. So when we say, okay, do this maneuver or do this turn, there is some internal processing happening in the car, and then it actually actuates that in the final actuator, and there is a lag, which is also different for different brands. So all of these things are different. So to understand how these differences in cars manifest, let's look at this example. So these are three cars: the Honda Fit, the Toyota Corolla, and the Ram. All of them are quite different, as you can see the images. So let's focus on lateral movement, right? So let's assume all cars are moving at 20 meters per second. All of them have a 10-degree steering angle, and they're all traveling on a flat road. So this is the trajectory that these cars would take. So this is the y versus x. So if you start at the same position, this is what the cars would do under the same instructions. So I guess right now it's clear that we need to really understand what exactly happens when you give instructions to cars. So how do we actually learn these things? We learn these things using something called the vehicle model. So to understand the vehicle model, let's look at some high school physics. So you're turning, you're in a car and you're about to go to a turn. So this is the front view. So let's assume that the road is banked, and let's also assume there is some wind, because why not? So this is the top view of your car. So your four wheels and your front wheels are turning. So I don't know how many of you are familiar with car dynamics. So this is something that we call a slip angle. The angle between your direction of motion to your heading is called the slip angle, and that determines a lot of the dynamics of your car. So you can see that there are forces that act on the tires. So this is basically something called a bicycle model, which is you assume that your car is a bicycle, which is not a great assumption, but it really works. It's a simplified assumption of your car. And then this is where the center of gravity is, and then you have if you draw all the free body diagram and the forces that act on this object, you end up with something like this. So let's quickly go through this. It looks quite scary, but it's not. So what we have is the desired curvature that we get from the model and from the planner. We know the car has to do something, right, at some curvature, at some speed. So we have the yaw rate. If we make some very generous assumptions about cars and about our dynamics, we can find out from the state space equation we can find what the slip angle is to achieve this particular yaw rate. And when we know the slip angle, we can find the steering angle that you're required to like turn to achieve like the maneuver that you want to do. So this is called the vehicle model. So we have a daemon in openpilot called paramsd, which learns all these parameters inside that we spoke about, and then it learns like the dynamics of your particular car. So it learns things like the steer ratio, the tire stiffness, the road roll, the steering angle offsets, and all of these things. And it learns all of these things about your car, about your particular car. So the interesting thing is that the steering angle offsets is basically, to go straight, you would assume you should keep your steering angle at 0 degree. But that's not true. All cars have some offset. You have to keep your steering angle at like 2 degrees or minus 2 degrees or whatever. And that depends on your car and how long you've driven it and stuff like that. So this is also something that we learn live while you're driving. A fun fact is that as a consequence of learning all this, we also know when you have a bad wheel alignment, which is if your wheels are aligned badly, and then if you want to go straight, you have to hold your wheel at like a 10-degree angle or something like that. A lot of people come on Discord and they're like, hey, I just installed openpilot. It drives fine, but it tries to go, when the wheel is straight, it tries to go right, and when it's going straight, the wheel is slightly to the right. Is my device broken? And then we tell them what the problem is, and then they come back a few days later saying, hey, about that, I went to a mechanic and he said my wheel alignments were wrong, and then they fixed it, and now my car drives perfectly. So this is something that from your logs and from the tolerances that we know, we can tell you if your car has a bad wheel alignment. Okay, so now we learned all of this stuff. So where do we actually use it? So as you see, we have sensors, which is car agnostic. We have models and planning, which is also pretty much car agnostic. But the actuators are specific to cars. So this is where we convert the car agnostic stuff to the car specific stuff. So we started with a maneuver that we wanted to do, which is like a steering angle. So to achieve the same thing, so we used a traditional PID control. So we have a steering angle, and the car gives us back the steering angle. So we're like, okay, go 10 degrees, and we have a classic PID control to make sure that the car is driving 10 degrees, and then everything is good. So this is the distribution of the lateral acceleration error when you're doing these maneuvers. So it's very important for us to understand how well the car is performing the maneuvers that you're asking it to do. And for that, we have a whole bunch of metrics. But one of the most important is absolute lateral acceleration error. So what do we mean by this? We mean that when the instruction is to perform some maneuver with some lateral acceleration, and the car is doing something else, so what's the difference between these two? And we have to drive this number down. So as you can see, the distribution is like the average is much lower than in turns, which means that while going straight, you're pretty much, it's like error-free, but in turns, it's slightly worse. So this is a metric. Just remember this metric. We'll keep coming back to this again and again. So we had all of this, right? But then we realized that in our fleet, the way we actually give instructions to cars, we don't actually give the steering angle. For like overwhelmingly most of our cars, we give the torque. We give the steering torque that you have to apply to the car. So we realized, wait a minute, we were going about this whole roundabout way of we have the curvature, we do all of these equations, and we find the steering angle, and then we close the loop on the steering angle, and then finally send torque. So we can just like circumvent that and then try to find torque. So this was a whole effort called torque control, which we released in 0815. So let's revisit the same maneuver that we did earlier, which is this car doing this turn at this angle. Now if you focus on the tire patch that is in contact with the road, so this is like the free body diagram of this tire patch. So you can see that these are the forces that develop on your tire during a turn. So you can see the wheel is heading is this, the wheel is moving here. So this is the slip angle. So what this effectively says is that the wheel torque is, you have a resultant force that is like X behind the center of the wheel. So basically, the wheel torque is this resultant force F times this pneumatic trail. And for a particular configuration of your car and your vehicle, this is constant. So the key insight here was that the wheel torque is proportional to the lateral acceleration that you want to achieve, adjusting for gravity. And from data, the second insight was that the wheel torque is directly proportional to the steering torque that you apply when you account for some friction. And friction is, when you're turning right and immediately, if you want to turn left, there is like a bit of friction in your steering column that you have to account for. So basically, we can get the wheel, we have a lateral acceleration that we want to achieve, and all we need to do is learn one proportionality factor to directly, to know what command to send to the car. This was great news. So we can find one value which for each platform, and everything is good. We implemented this. So you can see this is the lateral acceleration that is desired, and this is the steering command that we send to the car to achieve this. And this is for a Toyota RAV4, and this looks pretty linear to me. So this is what we implemented in 0815 and torque control, and then this is the result. So again, the same metric, absolute lateral acceleration error for some cars, Toyota Prius, and you can see that the torque control was much better than the simple PID tune for this PID on directly the steering angle. So this was great news. And this is even great because the subtlety is that these higher errors lead to other things that are undesirable, like they lead to more ping-ponging, they lead to like wandering in the lane, they lead to other things like that, which we don't want. So this was great news, and everything looks good here. But then, okay, let's revisit the assumptions that we made. The assumption was the pneumatic trail was like constant for a given vertical load, which means for a given configuration of your car. But then, like even among platforms, even among like Toyota Priuses, like each Toyota Prius is slightly different depending on like how long you've used it, what you put in your car, and stuff like that. The contact tire patch is also quite different. It depends on your quality of your wheels. It depends on how much air you have in your wheels. It depends on which road conditions you're driving on. And the steering column friction depends on the wear and tear of your car and etc. So this is also corroborated by the fact that when we do the same calculation to find the single factor for each platform on every car of that platform, we see that there is like a big difference in the big distribution in the value that is learned. So these are this is the distribution of the factor that I spoke about. And you can see that for even one platform, there is a wide range of values. So we set the value somewhere here in between, and then it's great for people whose cars are like here. But then if people's cars are like here or here, I mean, it's not that great. So this was like the motivation for us to go down this route of, we're not happy with platform averages. We want something tuned for your specific car, the car that you drive. So this inspired this effort called torqd, which is auto-tune. So basically what it does is the same thing that we were doing offline on like all the data from a particular platform like the RAV4. Now we do the same computation on your device while you're driving. So when you start driving, we collect data, and then once it meets certain conditions, we use the algorithm that we were doing offline in your car, and then now we have one constant that is learned on your car. And the great thing about it is that if you change your tires next week, or if you refill air, or whatever, if like you put some stuff on top of your car to go somewhere, like it learns live and it adapts live, and then your performance becomes better as a result of that, which is great. So going back to the same metric, so this is for Toyota Highlanders. You can see that the torque control was red, which was already an improvement over the previous generation stuff. But torqd was an even better improvement over that, which is great. This means that if your platform has like a bunch of versions where like the versions are different, but they somehow called it the same platform, it's still fine because we don't care about that, and we learn it for your particular car. So let's revisit the assumption again. We assume that the wheel torque is linearly proportional to the steering torque. So we assume that you apply some steering torque, and the wheel torque is some factor of that, and then we forgot about it. But turns out that's also not true. We assume that there are effects like backlash. So when you're turning left, and when you're turning, and immediately you have to turn right, there is some play in the steering column. There's like a backlash that you have to overcome, and then your car starts turning right. While driving, we don't really realize this because humans are really good at driving. But when you're controlling the car through instructions, you realize, there are all these effects at play that you have to account for. The other assumption was that we didn't care much about speed. We assumed that everything works the same at all speeds, like that's fine. But turns out this is also not true. For some platforms, at different speeds, your car behaves very differently. And this also needs to be accounted for. So for example, if you take the same plot of the lateral acceleration that we desire versus the steering command that you input, this is for the Chevrolet Bolt. I mean, this looks pretty nonlinear to me. If you remember in the RAV4, it was pretty linear, and in this, it's not. So we had to do something about this because if you apply the same algorithm that we used earlier, people have not nice experiences, especially at the extremes where it's it gets pretty nonlinear. So we implemented a nonlinear algorithm where we have a nonlinear fit for the relationship between this lateral acceleration that you want to drive on and the command that you give. And then this was out in 093. And you can see the effect of this change. So the nonlinear is better than the linear, which is also great. And a fun fact is you can see that there is a difference in the left turn and the right turn. This is like an idiosyncrasy of GMs. And all these are super interesting things because we can see this at scale. And it's very hard to see this if you have one car. But you can see that the errors are slightly higher for left turns than right turns. It's because in Chevrolets, the left turn is slightly different compared to right turns. And I mean, I don't know why, but it just is. And this also we need to account for. This was like a great improvement for the people people who have Chevrolet Bolt. So where do we go from this, right? We've seen that, over time we keep improving this stuff. We keep making sure that we move from fleet averages to platform averages and from platform stuff to each individual cars. So a big effort for that was we released this dataset called commaSteeringControl. And this dataset is the largest dataset of its kind. So what it has is the actual command that you give to the car, which is the steer command, and all the other metadata like the lateral acceleration, the road roll, the velocity, a whole bunch of other stuff. Now this is excellent because this data is something that probably nobody else has. We are in a unique position to have so much data about so many different platforms across different driving conditions, different weather conditions and all of that stuff, and different usages. The cars have different wear and tear. So this is a fantastic data set, which with all this data. So what you can, and this is 12,500 hours of open-pilot driving, 10 plus car models and 10 plus brands. And we have plans to add more data to this. We have plans to add non-open pilot driving. So when I spoke earlier about the vehicle model, that vehicle model is valid for small slip angles, which I mean by small steering on a highway. But if you want to do a rapid 180-degree turn, the vehicle model completely breaks down. You can't use the same vehicle model for that. In open-pilot, we are not there yet to do 180-degree turns, but we will be. And at that time, we will have to dive deeper into the data and figure out how we can improve our algorithms to cater to those maneuvers. So this data set has all of this information. So some people on Discord have already started using this. So they have some obscure brand that not many open-pilot users use. So now they have access to a whole lot of data that they can dive into, and they can see if they can improve the performance of their own particular car, which is great. So what is the future for tuning and controls, right? So we want to use more neural techniques to learn the complicated feed-forward functions. So you saw we started with a simple linear model, and then we went to linear model on device, and then we went to a nonlinear, but with still we sort of reverse engineer the function and then we learn it. But we want to move to a totally learned function. So what this means is there will be irrespective of what the input and output is in your car, we should be able to learn the response of your car to the instructions that we give to the car at all ranges of speeds. there are some cars that do automatic roll compensation in the car and all of this stuff. We want to be able to learn all of this stuff live in your particular car. Not sure what happened there. Yeah, so I mean that was like I was about to end. So so that's the that's like another plan that we have. The final goal is to move to like a target audience of 1. So basically the target audience of like you, and like everything is tuned to your car and it drives perfectly. Like the output of the model and the planner is perfectly implemented on your car, and you know there is, and then the final goal is me not getting any more messages on Discord saying, "Can you tune my car?" So that's it. I just had a couple of call-outs. So do check out this data set. Do come on the Discord channel, and we keep discussing a lot on the Discord channel. So you know, hopefully you can improve your own car much better, and then we can upstream it. That would be great. And a call out to openpilot user Twilsinko. He's been like at the bleeding edge of a lot of this stuff. I just wanted to call him out and say that's like great work, and we keep watching it, and we're very inspired. And I hope this also inspires more people to check out what's happening inside their car. That is great. Awesome. Thanks. Guys have any questions?
All right, we got lots of questions in the front.
So are all platforms using the torqd already for the automatic tuning, or that still needs to be fleshed out?
So all Toyotas, all Hyundais. So I think it's about 80% of our fleet uses it. The Hondas don't, because there is like there is a little bit of problem with the Hondas. I mean, they also work really well on traditional PID control. Yeah, I mean, most cars use it, and the plan is to roll it out to all cars.
Great.
Hello. So is longitudinal going to be in the foreseeable future for auto tuning?
Yeah, so that's a good question. So the thing is, the lateral tuning was very much a function of, like, it's very much defined by the vehicle model and the physics behind it. And a lot of the issues that we used to have was not handling the physics properly. But the thing with longitudinal tuning is that it's not much as physics as much as there is a lot of lag, and we don't handle the lag compensation properly in longitudinal, and it's like a bit tricky to go over that. So the problems that are with lateral tuning is very different from the problems with longitudinal tuning. So, I mean, yes, to answer your question, yes, we will have all the parameters learned live in the car, but it won't be part of torqd. Like that's like separate. I mean, it's like doing something else. There will be something else like that, which will learn all the parameters required for longitudinal.
Gotcha. Thank you.
Great.
I think my question is kind of similar to the last question, but how do you deal with like hysteresis, which is like basically actuator lag? Like for longitudinal, you said there's not much been done yet, but for latitude, like is it compensated for in the motion planning, or like?
Yeah. So so what we call friction is like is a manifestation of this hysteresis effect, which we already handle in openpilot. In torqd, we already compute what this the hysteresis component looks like, and we already handle this. So if you see the plots, I don't know if Greg can pull something up. So we have oh yeah, if you see these plots, so this is from our from the data set. Can I just go 1 second? I think it's fine. Yeah, so if you see this, so this is from the data set that we released. So the effect there is all hysteresis. I mean, you see the width in the plot, right? And this is already accounted for in torqd. And you know, I mean, we have more effects like that, which are not exactly hysteresis, but they have this like sort of discrete jump type of effects, which is more stuff for us to handle. But yeah, I mean, hysteresis is handled in torqd right now.
What is the optimal model of tyre for openpilot 0.9 according to the data?
I mean, yeah, that's a good question. So I guess to answer that, there is an optimal model of a tyre, and there is a simple and useful model of the tyre, which is what we follow. If you ask for the perfect model of the tyre, I mean, you can find many textbooks on this one topic on like what is the
sorry,
optimal.
I meant like the make and model. Like,
I see,
like,
I see.
should we be using Michelin or?
Oh, I see, I get you, I got you. I'm not sure. The thing is, we don't, from logs, can get the model of a tyre, so I guess that's something that we don't have access to. But we certainly understand what sort of, like which platforms have like, what sort of effects in following our instructions, and that's something that we can comment on, but yeah, we don't have access to the make and model of the tyre.
All right, I got a question up front.
Is it on the roadmap to replace the current controls and tuning system with a completely end-to-end machine learning system?
Yeah, there is. But I guess it's not to replace, but to build on, which is, as George said, as everybody's been saying, I think iterative improvement is something that is like a core tenet at Comma. So we had something very simplistic, and then we moved to something a little more complex and a little more complicated, and then that's, I guess, the direction it'll be going in. We will have much smarter techniques that learn everything that needs to be learned, like while you're driving, and then yeah. So it won't be like a replacement as much as just building on what we already have.
All right, thank you. Give it up for Vivek.